So does anyone know some situations where this is in real life? Exponential E functions. A common one to study is population growth. So any thoughts what could be relevant to population growth at the current situation of the world? Yes, COVID-19 cases across the world. Okay, so if you look at pretty much most countries, their initial growth of cases is exponential. I can look up, it's quite easy, you just Google COVID-19 numbers. Let's say India. Okay, so this is the growth numbers in India. We've got the start to about July, where it's exponential. Interesting, actually. I find it interesting in America that it's going up and down, like sporadically. So let's focus on Australia today, because we're Australians. Okay? I'm going to focus on the very start of the curve. Okay, so let's just look up to from the 10th of March to the 24th of March. Okay, so I'm going to focus on those. Now, have you guys looked up, there's so much maths behind the COVID-19 numbers. Have you guys looked up any on YouTube? The biggest thing about all of these examples is you either have a growth rate or a decay rate. If it's a growth rate, it's positive. If it's a decay rate, it's negative, okay? So we're going to look at a growth rate. I'm going to try and figure out the model for Australia's exponential start, okay? And what could have happened if we just left it, okay? COVID-19 cases started at 21 people on the 10th of March, and it was growing exponentially until the 24th of March, where it hit 430 cases. We want to determine the equation. So the 2 points is, let's say we have a Cartesian plane and it looks like this. The starting point, what was the value of, if that was time in days, what was the t or the x? 0. Okay, so the 10th of March is the 0 start date. Okay, and at that start, the y-axis or the number of cases was 21. Okay, what was the second point in the information or in the graph? Over here, this point in the graph. Yep, 14 days has passed, and how many people? 430. Okay, so most of these real-world exponential equations look like this. So they look like, population or number in terms of time. So I'm going to say the number of cases n, number of cases in Australia is equal to, and usually the initial, let's call it n0, is at the start of the equation. We then have the e. You guys remember what the e is, hopefully. We've been doing it the last 2 weeks. Then we have the growth rate up the top. So let's call it r, and the time. So the time could be years, could be seconds, could be, in this instant, it is in days, okay? So number of cases is n, n0 is the start amount, and it's always the thing in front of e, okay? Because you think about it, e to the power of 0, like 0 times past, what's e to the power of 0? 1. So you're just left with n0 or p0 or whatever it is at the front. Does that make sense? So this coefficient in the front of e is always the start. In our example today, what's the start? 21. Okay? Do we know the growth rate? Does it tell us? It doesn't tell us. So R is the growth rate. Because it's growth, it will be positive. Is there any questions so far? Probably the working to show that it's 21. You make nt equal to 21, like that. So you sub in the point, like that. Does that make sense? So therefore n0 is 21. So that's how I know n0 is 21. That's what I was just explaining before. We need to find the growth rate. So I've put in 1 point. What do you think I should do to find the other variable? Put in the second point, yeah? So let's put in nt is equal to what? 430 is the next y value or nt value. We just found what n0 is. What was n0? 21. We don't know what r is. Do we know the time when it's 4:30? 14. Yep. Okay, so we want to get r by itself. What's the first step? Divide by 21. Okay, then what? We want to get rid of the e. What's the opposite of e? What's the inverse of e? Natural log. Okay, so we're going to do natural log on both sides. We're doing natural log because that gets rid of the e. Because if we have log base and that number is the same, they cancel out. You guys remember this? Hopefully. So one more step to get r by itself. Perfect, nice. You can write log e as ln as well. I'm hoping you're getting used to the natural log or the different ways it's written. .21. Oh, I have a terrible memory. 5662, which is the same as 21.57%. Okay, so now we have our equation. Yes, that was just A. Now that you've got the equation, which is the hard part, you can do the rest pretty easily. But I just wanted to really show you that this is a real life thing. Like you can model stuff in real life with an equation like this. Okay, it's not just your maths classroom. Okay, so let's have a look. What's part B? When was the first 100 cases? So when did Australia reach the first 100? So part B, what are we going to do? First 100 cases. What's that? Is it N or is it T? It's N. Yep. And we're trying to find T. So same process as we just did, yeah? Trying to get T by itself. Do the log E of both sides, 8, according to this model.
On the 17th of March.
So if 7 days is 10 of March plus 7, and we've got a decimal, is it the 17th or is it the 18th? All right, so we've got 7.23 days after the 10th of March. So this is on the 8th day after, which is the 18th of March. Do you want me to have a look? There you go. Surprise. Okay, so the rate of increase when there was 100 cases. So we're using derivatives now. dn dt. Yeah? Or you guys might have seen it like that. Yep. Okay, so now we have to find the derivative of our function here. What would the derivative of that function be? Perfect. You bring the coefficient in front of t out the front. Do you remember do this? Yep. 2157 times, what was it? 21e to the 0.2157t. So remember, the e function stays the same. Nothing happens with the power because of my amazing first principles e thing, but you bring the coefficient out the front. Okay, next, it wants us to find out when it's 100 cases. So we simply do what? So we sub in 7.23, and that will give us the rate. So how much it's increasing. Times by that at the front. Okay, so what does that number mean? Yep, so in one day it'll increase by that much. Does that make sense? That's the rate of increase at that point in time. There's 30 days in April, there's 31 in March, by the way. So, in case you haven't figured it out, there will be approximately 51 days after the initial 21 cases. Okay? So you have to make, I guess, an assumption. You're looking at the 30th of April. Did anyone find out how many cases there could have been? 1.2 mil? I don't believe you, I'm going to do it myself. 1.2558. So that calc tells us E6, which is 10 to the power of 6. So aren't you lucky we didn't continue exponentially? Or aren't you grateful? So there you go. Real life exponential modeling. Okay?